Welcome to Lecture 8 on Subspaces and Immersions. This lecture should be a little bit shorter than the last one, so let's get to it. So, a natural question to ask is if you have a subset of a given set, in that set, the context in which the subset is found, it's superset. If its superset is a topological space, right, then can the subset be given a topology? And if so, in a natural way? And the answer is yes. A subset of a topological space can be made into a topological space, and the natural way to do it is with what's called the subspace topology. And it's defined simply as follows. If you have a subset Y of X, we can give it the subspace topology by simply stating that U, a subset of Y, is open if and only if there exists V open in X such that U is the intersection of V with Y. And I will prove that that's a topology, that defines a topology here, I think on the next page. But, so that's it. Now, sometimes we'll express this idea by saying Y is a subspace of X, all right? So if you say Y is a subspace of X, then contained in that statement is the assumption that Y is a subset and it's given the subspace topology, all right? That's the language. So here's an example. If you have R3 with a Euclidean topology, let me scroll down here a bit. R3 with a Euclidean topology, then if you have a surface inside the R3, you can topologize that surface using the subspace topology. And so what happens is, what are the basic open sets in R3? Well, they're open balls, right? So any open set can be formed by a union of these open balls. So likewise, sort of the basic open set in S is the intersection of these open balls with the surface, which might give you some kind of like curvy oval thing. Or if S is horizontal, it would give you disks, right? Like open disks. And an arbitrary open set in S could be formed by like a union of these kind of intersecting ovally things. Because of course an arbitrary open set in R3 is formed from a union of open balls, right? That's the metric topology, all right? And likewise, if you had a volume in R3, you could also define like open sets by the intersection of open balls with the volume. For example, if you could imagine a one that's sort of centered at the corner here, it would eat into the volume a little bit, right? But then the other part would be outside the volume. So the intersection of the open ball with the volume would be some sort of like, I don't know, like a quarter of a cheese wedge or something. I think I'm hungry. But so you can also induce topologies on volumes as a subset of R3, and the open sets would look rather different. But in both cases, the open sets are defined by intersections of the open balls in R3 with the subset, right? And you could also have a line in R3, right? You could have, oh, excuse me. You could have a curve, right? You could have a curve in R3. That could be your set, right? And that would be a subset of R3, and you could define the subspace topology on a curve by looking at, the intersection of, the open balls with the curve. Annoyingly, I don't have an orange handy. Forgive me, I'm going to violate my color coding and my general prohibition against using pink markers in these lectures. So here's the open ball, right? And so the intersection would just be kind of like, we would just include the part of the curve which was along inside that open ball, And so, again, you could induce a topology on a one-dimensional subset of R3 by looking intersections of open balls with that one-dimensional subset. So whether your subset of R3 is two-dimensional or one-dimensional or three-dimensional, any way you slice it, you can define a topology on that subset using the subspace topology concept, all right? Although, of course, the open sets look rather different in these three different cases. Now, a little bit of set theory here. If you have C as a subset of X is closed, that means X minus C is open. And you might notice that the complement by the intersection is the complement, is the intersection of the complement. So here's the complement in Y, there's the complement in X. right? X minus V versus Y minus the intersection of V with Y. And it's easy enough to verify this set theory right there. If you don't believe it, you should prove it. All right. Here's a picture. Let me scooch this up a bit here. So what's going on is I'm thinking of X as the topological space, Y is a subset of it, right? V is some kind of open set in X, right? The intersection of V with Y is the open set in Y that V induces, for what it's worth. Okay, so here's the theorem that we can get from this set theory right here. If C is closed, well, rather, if, I don't need the if there, do I? Let me just get rid of that if. I think the statement's just fine without that if. Sorry about that. Fix it. Come on. Do your job. Have one job. All right, there we go. So C is closed, C subset of X is closed if and only if Y intersects C is closed in Y. And here's the proof of that. So if the intersection of Y with C is closed in Y, that means that the complement of Y by Y intersects C is open in Y. But what does that mean? That means that Y intersect, this is just that set theory right here, right? So Y intersect with the complement of X by C is open in Y. These are just equal as sets. This and that are equal sets. And then, but that means that X minus C is open in X, all right? And that's the definition of subspace topology there. And then, of course, if X minus C is open in X, that means C is closed in X, and there you go. So the closed sets in a subspace are precisely those that are formed by intersecting with closed sets in the superspace. So, moving along here, page number 2. So, if beta, or let's say if B is a topological basis for X, then if you take intersections of things in the basis with with Y, all right, for Y a subset. So this is, of course, we're again assuming here that Y is a subset of X, right? Otherwise, this whole thing is kind of silly. And not only does it form a topological basis for Y subset S, in fact, that is the topology which is then generated is in fact the subspace topology. And so that proves, of course, that the subspace topology is in fact a topology. Now, you could prove the subspace topology is a topology directly from going through the axioms, and that probably would be a good exercise, because in terms of logical efficiency, I don't think this is like the best way or anything. You zoom in a bit. There we go. So here we go. Since we're given that B is a basis, that means the union of the things in the basis covers all of X. And then by the distributive law, if you take the union of the intersections of A with Y, that's the same as the intersection of the total union over A with Y. But the total union over A is exactly X because B is a basis. And so X intersect with Y, well, that's just Y because Y is a subset, right? Any subset intersected with a larger set is just a subset. And as such, that shows that this family of sets covers Y. And also, if we look at two members of the family which intersect, then we can follow that if they intersect at X, that means that X is an element of A intersect B, where A intersect B are elements of the given topological basis for X. And as such, there is another thing in the topological basis, C, which is also containing X and is a subset of A intersect B, which then means that C intersect Y is in this family. And not just that, X is an element of that C intersect Y, and that's contained in the intersection, which is to say that the criteria for theorem 3.7 has been met, and so theorem 3.7 tells us that in fact this is a basis for a topology on the set Y, and it's easy enough to verify that the topology which is generated by that is precisely the subspace topology, right? Because if you think through it, the topology which is generated by this says that an arbitrary open set in Y is generated from unions of things of this form, right? But if you think about that in the distributive law, that means that arbitrary open sets in Y are formed from unions of things in A. But what are the unions of things in things like A? Well, that's unions of members of this topological basis for X. And so those are in one-to-one correspondence, of course, with the open sets in X, because B is a topological basis for X, which is to say that the open sets in Y are exactly those that are formed by intersecting an open set in X with Y, which of course is the definition of subspace topology. Now, I don't know, like, is that the best way to prove it's a subspace topology? Probably not. I think you probably would do better just to directly attack the definition of subspace topology from the axioms, right? Now let's just think about that for a second. So go back over here. Why is the subspace topology a topology for Y? First of all, Y is open because, let's see here. Because if you take X, right, X is open in X by definition. X intersect Y is Y again, therefore Y is open. If you take Y intersect the empty set, you get the empty set, right? So that means the empty set is open in Y. So it's got empty set, it's got the whole set of Y. And then if you look at the other two axioms for the topology, arbitrary intersection and finite union, you're going to be able to prove those as well because of the distributive law for set theory and the fact that X is given to be a topological space. So that'd be a good exercise to go through. But I'm going to move on here. I'm going to leave that as a homework exercise possibility. Although I don't know if I've actually assigned it. It would make a good test question though, right? Prove the subspace topology is a topology directly from the definition of subspace topology and theorems of set theory, and without the use of theorem 3.7. Okay, so anyway, proposition: the inclusion map from Y to X defined by I of A is equal to A for all A and Y. Well, that's the inclusion map, okay. The inclusion map is continuous. Moreover, the subspace topology on Y is the coarsest topology under which the inclusion map is continuous. So if we take U a open subset of X, then the inverse image of U under the inclusion map is nothing more than U intersect Y. So like, that's easy enough to verify. If you think about it, for example, if U does not intersect Y at all, then the inverse, if the inverse image of U, if you're mapping from Y over to X, and if U doesn't even have a point in Y, the inverse image of U would just be the empty set, right? So that's that case. And anyway, I invite the reader to prove this if you don't believe it already, but I think it's fairly obvious that that's true. And so as that is true, the intersection of an open set with Y, well, that is exactly an open set in the subspace topology, therefore the inclusion map is continuous. By the way, if U intersect Y was not open in Y, right, in some other topology other than the subspace topology, then that would mean that the inclusion map is not continuous. So in other words, if you have a set, if you have a topology for Y which doesn't at least include the open sets in the subspace topology, then the inclusion map is not going to be continuous, which is to say that it's the coarsest topology from which the inclusion map is continuous. All right, moving on here. Let's see here. Example 2. Kind of an example of examples, really. It's more of a theorem than some of my propositions, but whatever. Anyway, here it is. Suppose X with distance function D is a metric space, Y is a subset of X. Then basically what I'm saying here is you can restrict the distance function to the subspace in the natural way. Just basically only define it for things in the subspace. and that makes the subspace with the restricted metric a metric space. And not just that, the topology induced on Y by the restricted metric, that's precisely the subspace topology formed from the usual metric topology on X. Actually, this was already illustrated in example 1. Truth be told, if you were to study the distance function restricted to those, to those subsets, then really, if you think back about this, if you were to pick a center point here, well, if you center the ball such that the center is on S, and then look at the distance from that point on S, of a fixed radius, less than a fixed radius, then you're going to get the curved shape here. And if you just calculate distance for points on S, then that's the restricted distance function. So, example 1 was already illustrating the one I was looking at in purple. Come on, fingers, work. All right, so an open ball in Y comes from Y intersect with an open ball in X in the context of a metric space, all right? So not everything's a metric space as we talked about last time, right? But if it is, the concept of distance function and induced metric topology all play nice with the concept of subset, is what this is saying. So that's cool. Another thing which plays nice with the concept of subspace is discrete spaces. So a discrete subspace is what? It's discrete if and only if the subspace topology is the discrete topology. What that means, of course, is that every subset of the subspace is itself open. In particular, it suffices to say Z, a subset of X, is discrete if and only if for any particular point in Z there exists an open subset of X such that the intersection of U with Z is just the set containing Z, which is to say that the singletons are open in the subspace topology. So here's a concrete example. The integers are discrete in the real numbers with the usual. Unless anything else is said, this assumes that we're giving the real numbers the Euclidean topology, all right? So the integers are the discrete subset of the Euclidean line, but in contrast, the rational numbers are not discrete. You cannot find an open subset of reals which just contains that one rational number and not others, right? If you take an epsilon ball around a rational number, there are infinitely many irrational numbers inside that epsilon ball. If you learn nothing else in reals, that should have happened. Okay. Anyway, example 4, any subset of X with the discrete topology, right? So if you have X and it's the discrete topology for X, then any subset is going to itself be discrete. So in other words, every subspace of the discrete topology is discrete. That's pretty easy to see. Okie doke. Let's move along here. Come on. Come on. There we go. Page 4. Proposition 3.54. If we have X and Z topological spaces, Y is subset of X, and F is a mapping from Z to Y, then, the inclusion map composed with F is a mapping from Z to X, then all that said, if the inclusion map composed with X is continuous, then also F is continuous, and conversely. Okay, so this is like the most awkward possible way to write the sentence that I composed with F is continuous if and only if F is continuous in this context. All right, so I don't know, I just was kind of following Minetti and I was writing the sentence down. I'm like, why have we written it this way? It's just if and only if, okay? So here's the proof. Here's the forward implication. Suppose the composite of I with F is continuous. Then let V be a subset of Y, all right? So I'm trying to show that F is continuous, right? And I guess I should scroll back up a bit here. So we have a mapping from Z to Y, right? I want to show that F is continuous. I'm assuming that the inclusion would compose with F is continuous, right? So let V be a subset of Y. I want to show that the inverse image of this is open in Z. All right, so notice that I of V is equal to V again for any subset V of Y, since the inclusion map sends X to X and so forth. All right, so then f inverse of v is f inverse of I of v, right? Because I of v is equal to v. But I guess I could have gotten more, I could have been more to the point here. Like, this is unnecessary. I was just like, oh man, that's not quite what I want. And then I'm like, oh, wait a minute, but v is also equal to I inverse of v in this context. The inverse image of v under the inclusion map is also v. So what I really have is f inverse composed of I inverse of v, and then by the sock shoes formula for inverse images of maps, which I have proved in some previous lecture and or exercise, or you should know from Foundations of Math or something. Anyway, you can prove this. We have that I composed of f inverse of v is that. But I know that I'm assuming I composed of f is continuous. So here we have the inverse image of under a continuous map of an open set, and that therefore is an open set. So consequently, we've showed the inverse image of open is open for f, therefore f is continuous. And the other direction of this here proof is somewhat similar, I believe. So here it is. If f is continuous, let u a subset of x be open. Note that the inclusion composed with f inverse of u is by sock shoes again f inverse of I inverse of u. But remember that the inverse image of u is open in the subspace X, because we have that the inclusion map is continuous, remember? And so that's open in subspace Y, but we're assuming f is continuous, so we have inverse image of open, which is again open by continuity of f. So we have an open subset. So the inverse image of an open set is open. Therefore, the composite of I with f is continuous. So there you have it. So yeah, this is part of the reason topology is a scary thing to assign to the bulk of math majors, because there's lots of math majors out there who don't understand inverse image, and if you don't understand inverse image, topology is kind of hard to understand. So, but if inverse image is not if you have gotten over the hurdle of understanding inverse image, then all of a sudden topology becomes a little bit less scary. Anyway, so if Y is a subspace of X, a topological space, and if we have A as a subset of Y, then here's the deal. The closure of A in Y coincides with the intersection of Y with the closure of A in X. So the difference between closure of A in Y and closure of A in X is the closure of A in Y, it's going to be the intersection of all closed sets in Y which contain A. Closure of A in X, on the other hand, is the intersection of all closed sets in X which contain A. Those in principle don't have to match. In fact, they don't match. Here's how they work together. Here's the calculation actually. So actually, I think the proof will actually make what the theorem is saying even more clear. So let C be the family of closed sets in X which contain A. All right, but we know that the only closed subsets of Y are those which coincide with the intersection of a closed set in X with Y. So we can form the intersection. In other words, here, so C prime, a subset of Y, is closed if and only if C prime is equal to the intersection of Y with a closed set C in X, all right? This we've already proved. And, okay, so if C prime is the family of closed sets in Y which contain A, then we can form, let's look at this here. We can form the closure of A and Y by the intersection over C prime, a funny looking C, like let's call it curvy C prime, all right? It's the intersection of all these guys. Every C prime contains A, all right? The condition here is each one of the C primes, I guess I should probably write that. Nah, I should put up here C prime. A is a subset of C prime, right? And this is actually C is subset of A, truth be told. All right. So this intersection is literally equal to that, because every C prime comes with a corresponding C, which intersected with Y gives you C prime, right? But if we think about this, if C prime, so if A is a subset, if C prime is equal to that, then of course All right, if C prime is equal to y intersects C, then it follows that it must be that A is a subset of C. Because if you have a subset of the intersection, it has to be a subset of both. Anyway, so I'm saying C is subset of A follows there as well, if you think through it. Now I've cluttered my proof. Oh well, C subset of A. And that's not what I want to say. C is not a subset of A. Dummy. Other way around. A is contained in C. Golly. A subset of C. A is subset of C, right? And as such, we have that the, what do we have? The intersection of all closed sets which contain C, and so here C is, this is a family of closed sets in X, right? This is the intersection of all closed sets in X which contain A. That's exactly the closure of A in X. Whereas this over here was the closure of A and Y. So like I was saying, the closure of A and Y is equal to the closure of A in X intersected with Y. So there you have it. Lemma 3.56 is next. Again, we're in section 3.5 of Minetti. Let X be a topological space and Z a subset of Y, a subset of X, right? If Y is open in X, then Z is open in Y, if and only if Z is open in X. If Y is closed in X, then Z is closed in Y, if and only if Z is closed in X. And if Y is a neighborhood, if big Y is a neighborhood of little y, then Z is a neighborhood of little y in big Y, if and only if Z is a neighborhood of Y in big X. And so we leave 1 and 2 to the reader. We'll look at 3. Let's look at 3 here. Okay, so suppose Y is a neighborhood of little y. All right, then there exists U open in X containing Y with Y an element of U, a subset of Y. That's what it means for big Y to be a neighborhood of little y. So in my picture down here, I've illustrated that by here's Y, and here's this brown circle U, all right? It's some open set which contains Y, and it's a subset. It's a subset of Y, right? But it doesn't have to have any particular relationship to Z, except that Z also contains Y. So Y is stuck here in that picture. All right, next up. Suppose Z is a neighborhood of Y, all right? If Z is a neighborhood of Y, that means that there exists a U tilde, which is a subset of Z, which I've made this blue dotted line here. See that blue dotted thing? That's the U tilde. So there's a U tilde subset of Z where U tilde is open in Y, all right? So here, Z is a subset of the subspace Y, so we're judging neighborhood by the subspace topology in Y. Okay, so U tilde is open in Y. And of course Y is an element of U tilde, which is a subset of Z. And since U tilde is open in Y as a subspace, that means that there exists U prime open in X, which I've made as this orange thing here. U prime open in X such that U tilde is the intersection of Y and U prime. All right? Erase my thought process here. My apologies for this editing break. There we go. Anyway. Okay, so then Y is an element of U intersect with U prime. All right? So what I'm trying to do here is I'm trying to find a open set in X which is containing Y, which is a subset of Z. That's what I need in order to show that, you know, Z is a, in order to get the, this implies that. So I'm trying to show that Z is a neighborhood of Y in X. All right, I got that Z is a neighborhood of Y in Y, all right? But I want to show that it's a neighborhood of Y in big X. So I need to find an open subset of X which contains Y and is a subset of Z. And the way to do that is just to intersect the brown circle with the orange circle. Not that they have to be circles, of course, but they're open sets. And the intersection of open sets is open because it's topology. And they're both open. The key is they're both open subsets of X, which means that the intersection of open sets in X is open. You got to be careful. You can't intersect an open set from the subspace and the superspace and assume that it's going to be open necessarily in this context, because that's kind of the thing we're trying to prove. Let me get back to the track here. So U intersect U prime, that is in fact a subset of U tilde, right? So because U tilde is the intersection of Y and U prime, so as such U tilde is a subset of U prime. Well, that's not true. Well, this intersection is a subset of U tilde anyway. Is it a U intersect U prime? That's in here. Well, it is a subset of U tilde in my picture, at least. Okay. Anyway, that's a subset of Z, which means that the intersection is an open subset in X, which is in fact proving that Z is a neighborhood of Y in X, because we found the open set, which contained Y and was a subset of Z. I leave the converse direction, that is that Z is a neighborhood of Y, implies Z is a neighborhood of Y in X, to imply Z is a neighborhood of Y in Y to the reader. Although I will say that this is only like a sentence, and it's like way easier than the part I just did. So you can look at Minetti. Let's see here. Finally, a continuous one-to-one map is called an immersion if every open set in X is the inverse image of an open set in Y. All right. So, in other words, F from X to Y is a topological immersion if and only if it induces F tilde from X to F of X, which he sometimes calls the restriction of F, and that's fine. And of course, this silly F tilde of X is just F of X in my stupid notation. And I don't always use tilde to mean the same thing. I'm just saying it's technically a different letter or whatever. Just changing the codomain from Y to F of X to make F tilde surjective. And so you got one-to-one, you got onto, and it's continuous. Therefore, it's a homeomorphism, because the inverse is also continuous in this context. So, good remark to make. Not all continuous one-to-one maps are topological immersions. Here's a good example of one that doesn't work. You look at the identity map here from the reals with Euclidean topology to the reals with the trivial topology. The trivial topology is the topology which just has open sets, empty set, and the whole real line. Well, the inverse image of the empty set is empty. The inverse image of the real line is the whole real line under the identity map. And there are many open sets in the Euclidean topology for R besides just the empty set and the reals. So clearly the identity map here is not a topological immersion. You can also talk about closed immersions and open immersions. A closed immersion is an immersion which is also a closed map. An open immersion is an immersion which is also an open map. To say something's an immersion, to say something's open means it maps open to open, right? To say something's closed, it means it maps closed to closed, right? So, like, the condition of open or condition of closed is stronger than just continuous. There's lots of continuous maps which are not open or closed. Okay, so lemma 3.59, let F from X to Y be continuous. If F is closed in one-to-one, then F is a closed immersion. If F is open and injective, then F is an open immersion. So here's like the proof of, I think, 1. So if F is one-to-one, continuous and closed, right? Suppose that. Then if C, scooch up a bit here, if C is a subset of X is closed, then that means F of C is a closed subset, because we're assuming F is a closed map, so the image of closed is closed. Then that means F of C is a subset of course, the range. And so you have that F of C is closed in the subspace, and consequently f from x to f of x is continuous, bijective, and closed, which is to say that f is a closed immersion. So anyway, sorry if I was hurrying a little bit through this. I don't think these things are terribly complicated. If you're not following me, I would urge you to, just take a page and write it out for yourself and see that it's true. I think it's fairly obvious. Anyway, moving on here. Next up is, I think, topological products, and then Hausdorff spaces. So I'm hoping to get those done a little bit later today. But I got a birthday party I got to go to at the moment. So see you guys in a bit.